Hello ladies and gents. Today we're going to be looking at what makes some acids strong, some acids weak, and we're going to be looking at what pH actually is. What does it mean? We are going to be doing some maths this week, so make sure you've got your calculator at the ready. You can follow along with some of the maths as we go. We're going to be using logarithms, so if you are a little bit rusty on them or you don't have a clue what they are, I suggest researching that, finding out a few details about that before you start watching this video. Okay. So these are the specification points. There's quite a few. This little line here is not actually a specification point. That is an assumption you're allowed to make in an exam. It probably doesn't make any sense at the moment, but for a weak acid you can assume that H plus equals A minus, and that H, we're going to be talking about this as we go through the video, so don't worry about it right now, but that is an assumption you can make in exams. Okay, let's get started. Strong and weak acids. When you dissolve an acid in water, obviously it dissociates into ions. You can think of that as H3O plus ions, or just H plus ions, and A minus ions. If you put a strong acid in water, like hydrochloric acid, sulfuric acid, nitric acid, it will dissociate pretty much as close as it possibly can to completely into ions. Okay, so you don't have any HCl molecules left, any covalent HCl molecules left when you put it in water. They all go to H plus and A minus. A weak acid, like like ethanoic acid or any other organic acid, won't dissociate fully. There will be quite a lot of ethanoic acid as a covalent molecule left. You'll have some H plus, some ethanoate minus, but still more ethanoic acid molecules left. The difference between a strong acid and a concentrated acid is a concentrated acid means there's not very much water to dissolve. You dissolved a lot of acid in not very much water, and a dilute acid means you dissolved an amount of acid in a lot of water, and that doesn't necessarily mean that a concentrated weak acid will be stronger than a dilute strong acid. It could be the other way around. We're going to talk about how you calculate that a little bit later. Anyway, to make things a little bit more scientific, we use Ka, a constant, to quantify the strength of an acid we're using. So if we look at this equation for the dissociation of ethanoic acid in water, you can see that there's an equilibrium, so we can set up the equilibrium equation. And the equilibrium constant, rather than calling Kc, we call Ka, because it's an acid, where we've got on the top the products being times together, and on the bottom the reactants, just like a standard equilibrium constant. If you've got big Ka, that means we've got a lot of most of it is on the right hand side of the equation, therefore we've got a lot of H plus ions. It's dissociated a large amount. If you've got small Ka, that means it doesn't dissociate very much in water. Simple. So that moves us on to pH quite nicely. So pH is a logarithmic way of measuring the concentration of hydrogen ions in solution. So if you imagine our concentration of hydrogen ions, that is going to be quite a large number. So, well, not necessarily a large number, but it's going to be a number that's hard to deal with. To work out pH, we take the negative minus log of the concentration of H plus ions. So for example, if we have a solution of HCl, that is 0.1 mole per dm cubed, we know that HCl dissociates fully when we put it in water. So we're going to have 0.1 moles mole per dm cubed of H plus ions. It's going to fully split up, so we're going to have however much we put in, we're going to have that many H plus ions. The negative log of 0.1 is 1. A logarithmic scale means that each time we increase our pH by 1, the concentration of hydrogen ions has increased by 10 times. Well, it would be increased by 10 times, but it's a negative log. Therefore, every time we increase our pH by 1, we decrease our concentration of hydrogen ions by 10 times. So every time we decrease pH by 1, we increase the H plus ion concentration tenfold. It's just the opposite way around to what it should be because we put that minus sign in there. Okay, pKa is very similar to pH. It is the negative log of the dissociation constant of our acid. The reason we use that is because it relates better to pH, and it's a smaller number. It's not some big sort of times 10 to the minus 4 number or times 10 to the minus 8 or whatever it is. It's just, it will be between 1 and 14. and it tells you in terms of numbers that relate to pH how much your acid will dissociate. So if you've got a very low pKa, it means it's going to dissociate a lot. So the pKa of a strong acid is basically going to be very, very low. So we can use all these numbers together to calculate pH. So strong acids are easy to work out the pH for. You can assume they completely dissociate in water. So HCl here has gone completely into H plus and Cl minus. So if we had 0.05 moles of HCl, we're going to end up with 0.05 moles of H plus. So the pH, if we do the minus log of 0.05, is 1.3, which we can do a little check in our heads. Does that sound like a reasonable pH for a strong acid? Yes, it's a strong, very highly acidic pH, therefore probably right. Bit more complicated for weak acids though. They don't fully dissociate, so we have to use their Ka and their Ka equation. So if we've got 0.05 mole per dm cubed of ethanoic acid, and the Ka constant is 1.7 times 10 to the minus 5, we can start subbing numbers into this equation. So this is the Ka equation. Now, if our ethanoic acid is dissociating, we can assume that, well, we don't assume, it's true, that H plus, the concentration of H plus will be equal to the concentration of CH3COO minus, because they split up equally. You know, for every mole of the H plus we get 1 mole of this. So we can just say that CH3COO minus equals H plus and substitute that in. So we get this equation. So we've got concentration of H plus squared over the concentration of ethanoic acid undissociated. Now we make an assumption. What we're going to assume is that the CH3COOH, the constant, doesn't dissociate very much. We're going to say it dissociates so little that the concentration of CH3COOH is the same as the concentration we started off with. It's a pretty big assumption, but it actually makes very little difference. It doesn't dissociate very much at all. So we sub that in. We find our concentration of H plus is 9.2 times 10 to the minus 4, and therefore our pH is negative log of that, which is 3.03. Sounds reasonable for ethanoic acid, quite concentrated. Okay, I'll go through this a couple of times because this is a calculation you will find yourself doing quite a lot. Make sure you're comfortable with all of the terms. We will be practicing in class. Final thing to talk about is a little bit complicated. So water also dissociates a little bit into H plus and OH minus. The hydrogen ion concentration from dissociated water at room temperature is 10 to the minus 7, which is why the neutral pH is 7, because minus log 10, base 10 of 10 to the minus 7 is 7. So if we look at the equilibrium of this reaction, we see H plus times OH minus over H2O. This H2O is so big we can assume it's part of the constant, so we can just move this up here and assume it's part of the constant. So then we get this thing called the water product, and the water product is really important. It's why the maximum pH is 14, because what it says is that the concentration of H plus times by the concentration of OH minus is always 10 to the minus 14 at room temperature. And we can use this knowledge to calculate the pH of bases, and this is something we're going to be talking about in future, not right yet. So have a little look through what we've just done. Check in your textbook if you need to. Have a look at any questions in there that might help you out if you're a little bit stuck. Make sure you've got all your key questions and summaries done, and we shall talk about this on Wednesday. Thanks very much for listening.